One of the things that you may remember from our very first video on exponential functions, so 2 videos ago, is that when we graphed 2 to the x and 3 to the x, so I redrew 2 to the x here, we noted, hey, this function is 1 to 1. And at the time, we noted it sort of as a curiosity, but now I actually want to delve into this a little bit more. So down here in red, I have noted a function is 1 to 1 if. So again, if you remember, say it with me as I'm writing it. No two inputs map to or correspond to the same output. Okay, so in other words, if f of a is equal to f of b, the only way that's possible is for a to be equal to b. So in fact, that arrow needs to be double pointed. We don't need to talk too much about that particular, but in fact, it does need to be double pointed. One thing that we see in the graph is that a function that's 1 to 1 will pass the horizontal line test. Okay, so you might remember that in order for a correspondence to even be a function, you can't have one input going to more than one output. So that's the vertical line test, right? We look at the graph, and if no vertical line crosses it in more than one place, you're looking at the graph of a function. A 1-to-1 function restricts that further, where if you take a graph of a function, so it already passes the vertical line test, and it also doesn't cross any horizontal lines in more than one place, then it's also 1-to-1. So if we look here and we draw in a bunch of horizontal lines, right? You can draw in as many as you want or as few as you want. Pretty quickly it becomes convincing that none of them will cross the graph in more than one place. So this function is 1-to-1. Now you might be thinking, why is she making such a big deal about this? What's the big deal? Well, if a function is 1-to-1, it has an inverse. And so let's ask ourselves, what is the inverse of an exponential function? So here in green, I'm going to draw and talk about the inverse function, but I'm not quite going to say what it is yet. We'll have like a big reveal at the end where we define the inverse function. So remember, the big idea of the inverse is that it undoes what the original function did, and one image that we used to demonstrate this was the image of kind of sending everybody back to where they came from. So starting, for example, with the point 0, 1, what this point tells us is that the function f takes the input 0 and sends it to the output 1. That means that the inverse function is going to do the opposite. It's going to take the input 1 and send it to the output 0. For the next one, we have the point 1, 2. Well, the 1, 2 means that the function f takes the input 1 and sends it to the output 2. So f inverse is going to do the opposite. It's going to take the input 2 and send it to the output 1. Next point, 2, 4. The input 2 is sent to the output 4. So the inverse is going to take the input 4 and send it to the output 2. And one more, 3, 8 on the graph of f. The input 3 is sent to the output 8. So the inverse is going to take the input 8 and send it to the output 3. And so on, right? We could keep going in the right direction. So like 4 would have gone to 16 on the original function because 2 to the 4th is 16. So that means on the inverse, the input 16 would have gone to the output 4. So I'm saying that because I want you to notice it's going to keep on climbing, but very, very slowly. Let's look at the other side, though. So we have negative 1, 1/2. So f sends the input negative 1 to the output 1/2. So this is going to take the input 1/2 and send it to the output negative 1. Then we have The input -2 goes to the output 1/4. So the input 1/4 is going to go to the output -2. And so what you're seeing is the same exact shape with all the same points, but just with the x and y coordinates switched. So let's see what we see here, okay? So domain, range, asymptote. Well, you could either look at the graph or you could just remember the notion of what it means for two functions to be inverses. And you'll remember that the inverse treats the inputs of f as its outputs and the outputs of f as its inputs. So what you might remember from our inverses unit is that the domain and range of the two functions switch. So what was once the domain of the function f becomes the range of the function f inverse, and vice versa. The asymptotes too, right? So the role of inputs and outputs is switched. So whereas in the function f, the further out we go on our inputs, the closer the outputs get to 0. On the function f inverse, the closer our inputs get to 0, the further our outputs go down to -infinity. And this is what we call a vertical asymptote. So the asymptote in the case of f inverse is the vertical line, x equals 0. The only question that remains is, what is this function? And so this is an exciting moment, and I'm going to call it a definition. And it's in some sense the most exciting moment of this week. The inverse of the exponential function. So we'll start with just 2 to the x. And then we'll elaborate it for all bases. Is the logarithmic function log base 2 of x. So in this moment, we are defining what it is to be a logarithm. A logarithm is the inverse to an exponential. So everything that we talk about with logs, everything is going to stem from this idea. So the inverse of this function is log base 2 of x. So you'll notice there's a lot of similarity here. It's the same idea of bases. A log has a base just like an exponential has a base, and the relationship, the logarithmic relationship, is the same as the inverse, is the same as the exponential relationship, just backwards. So let me add to this definition a little more. Moreover, the inverse of the general exponential function f of x equals a to the x is the logarithmic function log base a of x. So the bases are the same. What I'm going to do to finish this video is I'm going to talk about sort of something that we've almost mentioned. This idea that the relationships, the correspondence that's there with exponentials is the same as the relationship with logarithmic, but backwards. So we call this exponential versus logarithmic form. So with exponentials, we take an input, let's call it b, and then the exponential takes the base a and raises it to that power. And we get a to the b, and let's call a to the power b c. Logarithms do exactly the same thing but backwards. So if we have the function log base a of x, rather than taking the input b, it takes the input c, which incidentally, that's a to the b, don't forget that, and then the output b comes out. So I just kind of want to say this here, the role of inputs and outputs is reverse. Okay, so if a to the power b is equal to c, that's the same as saying that log base a of c is equal to b. So any exponential expression can be written in logarithmic form. Any exponential relationship can be written in logarithmic form. In some sense, this is the biggest and most key idea that we're going to be using when it comes to exponentials and logarithms, but really everything in this lesson is super crucial. Exponentials and logarithms are inverses of one another. We're going to explore this and play with this more in coming videos. Stay tuned.